Good day, everybody. Today, we'll be talking about acids and bases. First, we'll be going over some properties of acids and bases, respectively. Then we'll talk about some typical reactions acids and bases can have. Next, we'll go into more details about acids and bases, including some calculations. Let's get started. Most people must have had some experience with acids. For example, when you first put a Sour Patch Kid in your mouth, it tastes sour. This taste is caused by a white powder coating, which is a mixture of citric acid and tartaric acid. The citric acid and tartaric acid from Sour Patch Kid combined with the saliva in your mouth, they produce H+ ions, which causes that kind of taste. You might have also heard some reactions acids can undergo. For example, James Bond often carries an acid-filled gold pen, and this pen is made of gold because gold is one of the few metals that is not dissolved by most acids. When Bond is imprisoned, he squirts some acid out of his pen onto the iron bars of his cell. With enough acid, it would be possible to dissolve the iron bars of a prison cell, but it would take more acid than the amount of that fits in the pen. So we can see here on the right side, a small piece of aluminum placed in the hydrochloric acid or HCl dissolves away in about 10 minutes. So let's summarize some of the properties of acids. The first two we have already talked about. Acids have a sour taste, and they also dissolve many metals, but not all metals. For example, zinc will dissolve in acid, silver will not, copper will not, iron, yes, it will dissolve in an acid. So we'll go into the details a little bit later on. The third property is acids will turn the blue litmus paper red. For example, hydrochloric acid is found in most chemistry laboratories. It is the main component of the stomach acid, and when you place the blue litmus paper into the hydrochloric acid solution, then it will turn red, as you can see over here. Let's look at some more examples for acids. Sulfuric acid is most widely produced chemical in the United States, and the annual U.S. production of sulfuric acid exceeds 36 million tons. So what do you use sulfuric acid for? Sulfuric acid and nitric acid are commonly used in the laboratory. Sulfuric acid and nitric acid are used in the manufacture of fertilizers, explosives, dyes, and glue. You can see a wide variety of applications for both sulfuric acid and nitric acid. Sulfuric acid is also contained in most automobile batteries. When you think about driving a car, you can also think about sulfuric acid, which is part of your automobile battery. Here's the structure for sulfuric acid. And the formula for sulfuric acid is H₂SO4. And nitric acid is SNO3. Hopefully you have already mastered these formulas. We talked about the naming for different acids and bases previously. For organic acids, we usually call them carboxylic acids. They are the organic type of acid. Organic acids. So where do we find the organic acids or carboxylic acids? We usually find them in the substances derived from living organisms. such as fruits. As acetic acid can be formed in improperly stored wines. The word vinegar actually originates from the French word vinaigre, which means sour wine. We also have some other types of carboxylic acid, including citric acid, which is the main acid in lemons and the limes, and the malic acid, which is an acid form found in apples, grapes, and wine. What about bases? What about properties of bases? Bases have the bitter taste. Acids have sour taste, right? Bases have slippery feel, and bases can turn red litmus paper blue. Remember, bases turn red litmus paper blue, and acids turn blue litmus paper red. And the bases feel slippery. The reason is because they react with the oils on your skin to form the soap-like substances. So that's why it feels slippery. Soap itself is actually basic, and its slippery feel is the characteristic of bases. Some household cleaning solutions, such as ammonia, are also basic. Bases are less common in foods than acids because of their bitter taste. Our aversion to the taste of bases is probably an adaptation to protect us against alkaloids, which is the type of organic bases found in plants. Please note, alkaloids are often poisonous. The active component of a hemlock, for example, is the alkaloid coniine, and their bitter taste warns us against eating them. Some foods contain small amount of base. Coffee is acidic overall, but bases present in the coffee, such as caffeine, imparts the bitter flavor. Here's the formula and the structure for caffeine. Let's look at some more examples for bases. For example, sodium hydroxide, NaOH, potassium hydroxide, KOH, and sodium bicarbonate, which is NaHCO3. Okay. Sodium hydroxide and potassium hydroxide are found in most chemistry laboratories. They are used in processing petroleum and cotton, and in soap and plastic manufacturing. Sodium hydroxide is the active ingredient in products such as Drano that work to unclog drains. Sodium bicarbonate can be found in most homes as baking soda and is the active ingredient in many antacids. When taken as an antacid, sodium bicarbonate neutralizes stomach acid, relieving heartburn and sour stomach. So far, we have talked about many properties and examples for acids and bases. But what is exactly an acid? What is exactly a base? So let's look at some definitions of acids and bases. The ARRHENIUS definition of acids tells us an acid produces H+ ions in aqueous solution. For example, in water, HCl will ionize to form H+ ions, or so-called proton ions, and the corresponding chloride ions. So when we write the equation, it's HCl, which is aqueous solution, it ionizes to H+ and the corresponding Cl- chloride. The H+ ions are highly reactive. In aqueous solution, they bond to water to form hydronium ion, or H₃O+. Chemists often use H+ interchangeable to the hydronium ion. So here's the structure for H₃O+ hydronium ion. When water reacts with H+, it produces hydronium ion. The Arrhenius definition of bases. A base will produce hydroxide in aqueous solution. Okay, for example, NaOH is an Arrhenius base because it produces hydroxide ion in solution. Molecular compounds containing an OH group, such as methanol, the formula is CH3OH. These molecular compounds do not dissociate in the solution and therefore do not act as bases. Similar examples have ethanol. This does contain OH, but this OH is not ionizable. It will not produce OH minus. So this is not an Arrhenius base. However, calcium hydroxide will ionize into calcium ion. AQ means aqueous solution, and corresponding hydroxide ion. So for this reason, calcium hydroxide is an Arrhenius base. Under Arrhenius definition, H+ can be used to represent the acid, and OH- can be used to represent base. And when they combine together, water is produced. When we compare the Arrhenius and the Bronsted-Lowry definition of acids and bases, we can find out the Arrhenius definition of acids and bases cannot explain why some substances act as bases even though they do not contain hydroxide. For example, according to Arrhenius definition, NH3 will not be a base because it does not contain OH-. Another example, for example, baking soda, sodium bicarbonate. We know we have used the baking soda or sodium bicarbonate as the antacid because it can serve as a base, but according to Arrhenius definition, it is not an Arrhenius base because it does not contain hydroxide, OH-. So we will have to find another definition which is more loosened up. That's the Bronsted-Lowry definition. And this definition focuses on the transfer of proton or H+ ions in an acid-base reaction. Since H+ is a proton, a hydrogen atom with its electron taken away, so this definition focuses on the idea of the proton donor and proton acceptor. In the Bronsted-Lowry definition, an acid is defined as a proton donor and the base is defined as a proton acceptor. According to this definition, HCl is a Bronsted-Lowry acid because in solution it donates a proton to water. Do remember, anytime if somebody is donating a proton, somebody else must have accepted that proton. So HCl donate a proton, which means it loses H+. So HCl, after losing H+, it will become Cl-. And that proton, or H+, is accepted by H2O. So H2O will pick up one H+, and it become H3O+, which is hydronium ion. Ammonium, which is not a base according to Arrhenius definition, but it is a base according to Bronsted-Lowry definition because it can accept a proton from water. Here's how that happens. NH3 ammonia accepts one proton from water and become NH4+. At the same time, since the proton comes from H2O, so H2O is losing a proton and become OH- hydroxide. As we have noticed, in this process we just analyzed previously, in this reaction between HCl and water, HCl it's serving as the proton donor or an acid. And the H₂O is the proton acceptor, so it is a base according to Bronsted-Lowry definition. Similarly, in the reaction between ammonia and water, H₂O is the proton donor, or it loses a proton to ammonia. That means ammonia is the proton acceptor. That's why it is a base according to Bronsted-Lowry definition, and the water is an acid according to Bronsted-Lowry definition. So as you might have noticed, in these two different reactions, water first serves as a base, but in a different reaction, it serves as an acid. I want you to pay attention to some other features as you see over here. This HCl, when it loses that proton, it becomes Cl minus. And this pair of species, they are called conjugate acid-base pair, and this is the acid. And when you lose one proton, it becomes the base, and this base is the conjugate base. So when we write HCl and the Cl minus as a pair, and this pair is called conjugate acid base pair. Similarly, when H₂O picks up the proton from H plus, it becomes hydronium ion H₃O minus, and H₂O serves as the base in this process because it accepts one proton, and H₃O is going to be called the conjugate acid. So this pair of conjugate acid base is hydronium ion and water. So that's two pairs of conjugate acid and base. Let's look into the same example for ammonia reacting with water. When ammonia gains one proton, it becomes ammonium ion. So ammonium ion is called the conjugate acid. So NH4 plus ammonium ion and NH3, and this is called a pair of conjugate acid base. Similarly, when H₂O loses one proton, it becomes hydroxide. So H₂O is called the conjugate acid, and hydroxide is the conjugate base. H₂O and hydroxide is also a pair of conjugate acid and base. Let's look at this from different perspective. When ammonia picks up one proton, or in another word, ammonia serves as the proton acceptor, it becomes NH4 plus. The structures are listed over here. And have you noticed the difference between NH3 and NH4 plus is only one proton, one H plus difference. Similarly, when you look at H₂O, when it loses one proton, or one proton is removed from it, it becomes hydroxide. And the difference between this conjugate acid base pair is only one proton. Let's look at another example. Sulfuric acid reacting with water. In this process, sulfuric acid serves as the proton donor, or it loses one H plus, so it becomes hydrogen sulfate. For this reason, sulfuric acid and the hydrogen sulfate, they are conjugate acid and base pair. Similarly, H₂O and H₃O plus, they are so-called a conjugate acid base pair. Let me write this down. Here's the first pair, conjugate acid base pair. Here's another pair, which is water and hydronium ion. let's work on a few problems. Which of the following can act as a Bronsted-Lowry acid? By definition, a Bronsted-Lowry acid can act as a proton donor, which means you can lose one H plus and generate something that will exist in water. And in other words, you will need to find out if or not these choices can lose a proton or H plus. Can this lose a proton? Can this lose a proton and generate something that does exist? When this one, ammonia, loses a proton, it becomes this. But this one does not exist in water. So this one is not going to be correct. And NaOH, if it loses H plus, it will become NaO. This does not exist at all. Carbonate does not even have H plus to lose. Okay. Bicarbonate, or so-called hydrogen carbonate, when it loses proton, it becomes carbonate. So this carbonate, as we know, it does exist in water. We have learned carbonate a long time ago. So for this reason, D hydrogen carbonate, or so-called bicarbonate ion, can serve as a Bronsted-Lowry acid, because after it donates that proton, it produces an ion that does exist in water. Which of the following is not a property of a base? It turns the litmus paper red. Base does not turn litmus paper red. An acid turns blue litmus paper red. A base turns red litmus paper blue. So A is not a property. According to Bronsted-Lowry definition, a base is a proton acceptor. It does feel slippery when you touch it. It tastes bitter as well. So A is the correct answer. Identify the two Bronsted-Lowry acids in the following reaction. So when you look at this equation, an acid, according to Bronsted-Lowry, donates a proton. Or when you look at a conjugate acid-base pair, so this and that's a pair. So this is the conjugate acid, and this is the conjugate base, because the difference between the two is one proton or one H plus difference. Now you look at the box, that's the conjugate base, and NH4 plus, that's conjugate acid. So we are asked to identify the two Bronsted-Lowry acids. It would be this phosphoric acid and the ammonium ion. So B is the correct answer. Basically, when you try to solve a problem based on definition, you must be 100% clear about the definition. A Bronsted-Lowry acid will have the ability to donate one H plus or a proton and generate something that does exist. A base will accept a proton or an H plus and generate something that does exist in water. What is the conjugate acid for this formula? So when you look at the definition, what is the conjugate acid? What's the difference between a conjugate acid and base pair? So conjugate acid and the base, as we know, the only difference is one proton. So for conjugate acid, it must have one more proton than the conjugate base. So what is the conjugate acid for this one? That means you must add one H plus to it and make a new formula. The original formula you see is copied over here. So you add H plus. When you add H, you will have 3 hydrogens. Do remember, it's not just H you add. You also add a charge to it. Originally, you would see a minus. But if you add H plus, that plus and minus will cancel, so this negative charge will not exist anymore. In other words, D is the correct answer. Which of the following is not a conjugate acid-base pair? That's the same question as what we just went over. The difference between conjugate acid-base pair is 1 proton difference. In other words, if you, for example, if you do take away 1H plus, can you generate the corresponding species NH3? Yes, you can. So this one is a conjugated acid-base pair, but we want to pick the one that is not. So you don't pick A. What about these two? Can you actually remove 1 proton and it become the next thing? Yes. When you look at this one, can you remove 1 proton and it become the next species? Yes, that's correct. Okay. What about this one? If you remove 1 proton, what's going to happen? Okay. So let's rewrite this. That's the formula. By the way, these formulas actually they do not exist. Okay, nitric acid would be this, but there's no species that look like this. But let's assume it does exist. So what's going to happen? If you take away 1 proton, what's going to happen? You take away that H. That means you have this. Now you're going to take away the plus charge over here. So you will take away the plus charge. It will become 2 negative. So you will have this as the species that is left, not NO3 plus. So for this reason, this one is not a conjugate acid-base pair. The next one, yes, when HClO2 minus an H plus, then you will see chloride produced. So this is also the conjugate acid-base pair. So for this reason, you pick the one that is not. D is the correct answer. The reactions between the acids and bases are called neutralization reactions. When an acid and base are mixed, the H plus from the acid combines with the OH minus from the base to form water. So that's exactly what you see over here. That's the so-called net ionic equation. As we have learned before, we have a molecular, this is so-called a molecular equation, and here that's the net ionic equation. Basically, you ionize the strong acids and the strong bases, you also 100% ionize that. On the right side, water is a non-electrolyte. It will stay intact. Potassium chloride is a soluble salt. That's why you have aqueous solution over here. So you also need to break it down into corresponding ions. And this equation is called complete ionic equation. We have learned this before. This is a review about this concept. This is complete ionic equation. And the first one, as we learned, if everything exists in the molecular form, we call this molecular equation. Right. Then if you cancel out these spectator ions, which do not change before and after the reaction, so you cancel this one out, you cancel K plus out, then that's what you have over here. You cancel out everything. That's a so-called net ionic equation. Right. Hopefully this review helps remind you of something we have already learned. The net ionic equation for many neutralization reactions is H plus reacting with OH minus, which produces water as the product. Some other reactions acids can include reaction with many metals. So for example, magnesium will react with an acid and generate corresponding salt and hydrogen. And sulfuric acid can react with zinc and produce hydrogen and salt. Hydrochloric acid reacts with iron and produce hydrogen and salt. So you might have noticed when the metals react with acids, they generate hydrogen gas as one of the products, and the other product would be the corresponding salt. Do remember, not all metals will react with acids. For example, copper will not react with HCl or dilute nitric acid or sulfuric acid. Silver will not react with dilute acids. Gold will not react with dilute acids, etc. We will discuss the way to determine whether a particular metal dissolves in an acid or not in Chapter 16. Acids can also react with metal oxides. That's the compound formed between metal and oxygen. The acids will react with metal oxide to produce water and the corresponding salt. For example, when an acid, hydrochloric acid, reacts with potassium oxide, it generates water and the corresponding salt, potassium chloride. When HBr, hydrobromic acid, reacts with the magnesium oxide, it will produce again the corresponding salt and water. So when you look at this reaction, it's basically like you combine inside and outside. So inside and outside, but you need to have the correct ratio. So inside and outside recombining. When H is combined with oxygen, it becomes H₂O, not O, because H₂O is balanced. When Cl combines with K+, Cl is Cl minus, and K is K+. So you're not going to write K2Cl here. Rather, you write KCl, because K, potassium, carries 1+ charge, and chloride carries 1+ charge. That's why the formula is KCl, not K2Cl. So when you recombine them, you must get the ratio correct. Similarly, when H combines with water here, with oxygen, it forms water, H₂O, not just the H and O combine. All right. Another thing is when bromine combined with magnesium. Okay, magnesium carries a 2+ charge, and bromine carries 1 charge. It's Br minus. So when you recombine them, it takes 2 bromine for every magnesium, because magnesium carries 2+, and the bromine carries a 1-. So it's MgBr2, not MgBr. Aluminum is kind of special because aluminum can react with an acid. For example, aluminum can react with HCl, and it will generate aluminum chloride and hydrogen as one of the products. Let's balance this equation. So this reaction is balanced. Aluminum, not only it can react with an acid, the special characteristic for aluminum is it can also react with a base such as sodium hydroxide and generate one product, sodium aluminum hydroxide, and hydrogen. So for this reason, if your household plumbing pipes were made of aluminum, it would not be safe to use NaOH, which is the main ingredient in Drano and other drain opening products. If you use this to unclog your drain, it's very unsafe because of the reaction of aluminum with NaOH, as you see over here. Aluminum can react with an acid. It can also react with the base, and zinc has similar properties. Zinc can react with an acid. It can also react with a base. Let's look at a few examples. What are the two products of the reaction between hydrochloric acid and magnesium oxide? Remember, an acid will react with magnesium oxide and produce magnesium chloride in the water. But how do you write the formulas? So let's write this equation. Hydrochloric acid will react with metal oxide, for example, magnesium oxide. You got to be able to write MgO first. Then it's inside and outside. When H combines with O, it's not HO. No, it's not HO. It's H₂O, so it's balanced out. And when Mg recombines with Cl, it's not MgCl, because Mg actually carries +2 charge and chlorine is -1. So for this reason, it takes 2 chlorine for each magnesium. So when you write the formula, you can actually balance this equation. This becomes the completely balanced equation. The product is water and salt. An acid reacts with a metal oxide. It always generates not hydrogen, but water and corresponding salt. When a reactive metal reacts with acid, it will generate hydrogen and the salt. So that's different. Please pay attention to that. So for this reason, the correct answer is C, not B. What gas is produced by the reaction between sulfuric acid and zinc metal? Zinc is a reactive metal. It will react with the acid, which produces the salt and the hydrogen as the products. We can write, of course, that means E is the correct answer, but let's write the full equation just for learning purpose. Sulfuric acid reacts with zinc. Remember, zinc is one of the active metals that will react with acid. Zinc, iron, magnesium, etc. This will produce the salt and hydrogen, and this reaction is already balanced. When an acid reacts with the base, it's called neutralization. Sometimes we're asked to quantify the amount of acid or base in the solution by carrying out this type of reaction. And this type of method is so-called acid-base titration. And the solution stoichiometry can be applied to a common laboratory procedure, and this is called titration. The stoichiometry just means use the chemical reaction to do the calculation. In the titration, a substance in the solution of the known concentration is reacted with another substance in the solution with the unknown concentration. In the acid-base reaction by hydrochloric acid and sodium hydroxide, as you can see over here. Okay, so this is actually not the net ionic equation. This equation is the molecular equation. The net ionic equation is H plus reacting with OH minus, which gives you water. So this is the net ionic equation. So please make the change over here. Sorry about it. So this one is the molecular equation, and the net ionic equation is the bottom one. In an acid-base titration, we slowly add a solution of the known concentration to the solution of an unknown concentration in the flask at the equivalence point, or when the reaction is over. Neither reactant is present in excess. Both are the limiting reagent because they react according to the chemical coefficients. They are reacting completely with each other at that equivalence point. The number of moles of reactants are related by the reaction stoichiometry, or it's the same as saying they are reacting according to the correct number of mole ratio according to the balanced chemical equation. At the equivalence point, the titration is complete because the correct number of moles of H plus and the OH minus are completely reacted. How do we know we have reached the equivalence point? This is usually signaled by a so-called indicator, which is a dye which will change color depending on the acidity of the solution. In most laboratory titrations, the concentration of one of the reactants is unknown and the concentration of the other is precisely known. By carefully measuring the volume of each solution required to reach the equivalence point, the concentration of the unknown solution can be determined. Of course, we will look at some examples. In this titration, the NaOH and HCl are reacting. So you write the equation NaOH reacting with HCl, which will generate the salt NaCl and water. When an acid and base react, it always generates a salt and water as the products. And this reaction is already balanced. So everything is a 1:1:1 ratio. When the reaction is complete, the added indicator, which is most commonly phenolphthalein, will change to pink. This tells you the reaction has reached the equivalence point. Then the titration is over. The reaction will have changed from colorless to a light pink color. The indicator phenolphthalein in acidic condition is colorless, but in basic condition it is pink. So that's why you see the color change. Let's look at one calculation. The titration of a 10.00 milliliter of HCl solution of unknown concentration requires 12.54 milliliter of 0.100 milliliter NaOH solution to reach the equivalence point. And we want you to calculate the concentration for the unknown HCl solution. For this question, we need to write the balanced equation between NaOH and HCl. And when they react, they generate NaCl and the water as the product. As we just talked about, when we balance this equation, it happens to be 1:1 ratio. And in other words, the moles of NaOH and the moles of HCl are exactly the same. And how do you calculate the moles? The moles can be calculated by molarity times volume, M times V. M times V is the moles. M times V is the moles. So for this reason, you can do the calculation by substituting numbers in. For HCl, the concentration is unknown, but we do know the volume. For NaOH, the concentration is given. So we substitute the concentration for NaOH in and also substitute the volume in after we do the calculation. The concentration for the unknown hydrochloric acid is 0.125 mole. Let's look at another example. What volume of 0.4590 mole of NaOH solution is required to reach the endpoint in the titration of a 20.00 milliliter sample of sulfuric acid? Remember, when you look at sulfuric acid, it's biprotic acid, which means when you do the reaction between sulfuric acid and NaOH, the ratio between the acid is 1, and it's 1:2 ratio for the acid and base. When you write this reaction, it will have the sodium hydroxide and water as the product. When you balance this reaction, here's what you see. In other words, the moles of sulfuric acid and the mole of NaOH in this case is not 1:1 ratio. Rather, you have twice as much of, so the moles of NaOH is twice as much as that of the mole of sulfuric acid, because you have the 1:2 ratio over here. So moles of acid can be calculated as M acid, M times V gives you the moles. And for the base, it's also M times V. Sorry, that's NaOH. OH and M times V. Do you remember the amount of base is twice as much as that of the acid? So this will be what you need to do. So we substitute the corresponding numbers in. For the mole of NaOH, the mole of sulfuric acid is 0.3669, and times V is 25.00 milliliter, and this is 0.4590 molar times an unknown volume. So we're going to do the calculation. VNaOH will be 39.97 milliliter. A is the correct answer. Let's do a quick summary about the calculation based on acid-base reaction. The key is to figure out the mole ratio of the acids and the bases according to the balanced equation. When you know the mole ratios, the moles of the acids and bases can always be calculated by M times V, M being the molarity and the V being the volume. Now let's switch gear and talk about the strong acids and weak acids, strong bases and weak bases. Let's first talk about strong acids. A strong acid is defined as the acid that ionizes 100%. Strong acid, what do you mean strong? Strong means 100% ionization. What is weak? Weak acid means partial or less than 100% ionization. You need to memorize the 6 strong acids. For example, HCl, HBr, HI, nitric acid, sulfuric acid, and the perchloric acid. The most famous weak acid is hydrofluoric acid. It does not ionize 100% in solution. Acetic acid is another example for weak acids. No matter if it's a strong acid or a weak acid, when they dissolve in water, they will ionize either 100% or partially. They will generate enough ions to conduct electricity. However, the same is not true for water. Pure water is not a good conductor of electricity because it has relatively few charged particles, or water will ionize to a very, very small degree. It does ionize, but it cannot produce enough or appreciable amount of ions to conduct electricity. So for this reason, pure water is not a good conductor of electricity. The ability to conduct electricity is the characteristic of so-called electrolytes, and those that do not conduct electricity are called non-electrolytes. Pure water cannot conduct electricity. This can be tested out with experiment listed in this figure. When pure water is used and the light bulb is off, even with a closed circuit. However, for HCl, which is a strong acid, it will ionize 100% to produce enough ions to carry the charges so it conduct electricity. So HCl is an electrolyte. Water is not an electrolyte, or water is a non-electrolyte. As we mentioned, we have 6 examples of strong acids, as we talked about: hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid, perchloric acid, and sulfuric acid. And sulfuric acid is the only diprotic acid because it contains 2 hydrogens in the formula. Remember, a strong acid is defined as an acid that ionizes 100%. In contrast, a weak acid will ionize partially. When you look at this equilibrium, HF will react with water and generate hydronium ion and fluoride according to BRONSTED-LOWRY definition of acid. When you look at this picture, when this dissolves in water, only small portion of the HF is ionized, and the majority of them will stay intact as the molecular formula HF. In other words, when HF dissolves in water, a very small, actually it's less than 5% of the HF is ionized. Let's compare the ability to conduct electricity of a weak electrolyte with water. As we have just talked about, pure water will not conduct electricity, so the light bulb is off. A weak electrolyte will conduct electricity, but the number of ions it produces is very small. So for this reason, the light bulb is not as bright as what you just saw for the example of HCl, which is a strong acid. HF is a weak acid. So HF, being a weak acid, only ionizes partially, producing less ions. So it's a weak electrolyte. We just mentioned hydrofluoric acid and acetic acid as 2 common examples for weak acids. We also have some other examples. For example, formic acid, phosphoric acid, carbonic acid, sulfurous acid, etc. Basically, you can assume, besides the 6 strong acids you have to memorize, everything else, if it's an acid, you assume them to be weak. The strong acids, the 6 strong acids, HCl, HBr, HI, sulfuric acid, nitric acid, and perchloric acid. You have to memorize all those 6 for your exam or test preparation. Let's do a few calculations based on the concept of strong versus weak. For example, 1.5 molar of HCl, we want you to calculate the hydronium ion concentration, or you can simply say what's the H plus concentration. Remember, HCl is a strong acid, so this ionizes 100%. For this reason, the concentration of hydronium ion will be exactly the same. which is 1.5 molar. For 3.0 molar acetic acid, we are not going to be able to calculate the concentration, at least not for now. In the future, when you advance to general chemistry, we will be able to calculate that. But for now, we do know acetic acid is a weak acid. It partially ionized. So we do not have exact information about what percentage of this will ionize. So the calculation of this concentration is beyond the scope of this text. As I said, when you move on to general chemistry 2, you will be asked and you will learn how to do the calculation for this type of weak acids. We just talked about some examples of strong and weak acids. What about strong bases? Remember, strong means it will ionize 100%. Strong means 100% ionization. Weak means partial ionization. So for this reason, similarly, a strong base is the one that completely dissociates in solution. You need to memorize some examples. Basically, they are from group 1A and group 2A, and they are hydroxides. Group 1A hydroxides and group 2A hydroxides. They are the examples of strong bases. Let's look at the picture to understand this a little bit more. When NaOH dissolves in water, you do not see any more NaOH. That does not exist. Everything has been ionized 100%. So you only see the corresponding ion, Na plus, OH minus hydroxide, OH minus, because they have ionized 100%. The opposite is true for a weak base, which ionizes only partially. When NH3 dissolves in water, most of them stay intact, but only a small portion ionize to the corresponding ions. You notice that in the box? Most of them stay as ammonia intact, but some of them, or a small portion of them, have ionized to the corresponding ions. There are many weak bases, similar to what we talked about those acids. You simply remember those typical examples of strong bases, and all other bases, you simply assume them to be weak bases. The most common weak bases, as we talked about, is ammonia, and the other bases are usually organic amines, as you can see, methylamine, ethylamine, etc. Let's look at some calculations based on bases. Calculate the OH minus concentration in each of the following solution. So when you look at KOH, first thing that occurred to you should be KOH, potassium hydroxide, is a strong base, which means it ionizes 100%. For this reason, when this ionizes, KOH ionizes 100%, it gives you 1:1 ratio of hydroxide. That's why the concentration for hydroxide is 0.35, the same as the original. What about 0.35 molar of methylamine? Methylamine, as we just learned, is an example as a weak base, which means it will only partially ionize in water, so we will not be able to calculate the exact concentration of hydroxide because we do not know the percentage of the ionization. So not enough information at this stage. Let's look at a few more examples. What is the hydroxide ion concentration in 1.0 molar calcium hydroxide? First, you got to realize the correct formula for calcium hydroxide is Ca parenthesis OH parenthesis 2, which means for each unit of calcium hydroxide. When this ionizes in water, you realize this is a strong base. You must memorize all those strong bases. A strong base will ionize 100%. When this ionizes, though, 1 unit of calcium hydroxide will produce 2 hydroxide ions because of this subscript 2 over here. So for this reason, if you have 1.0 molar of calcium hydroxide, you will have the concentration of hydroxide twice as much, because when you look at the equation, it generates twice as much. So it's 2 times of the original. So this gives you 2.0 molar. D is the correct answer. Next question. Each of the following pairs contains 1 strong acid and 1 weak acid, except, look at the first, strong, and weak. This is weak and weak. So this one is the correct answer. Strong and weak. This is strong and weak. Folks, you must memorize those 6 strong acids. Everything else, all the other acids, you assume them to be weak. That's how you can easily identify which answer is the correct one for this question. Next question. You have 0.25 molar solutions of each of the 5 substances below. Which of the aqueous solution is the best conductor of electricity? You got to understand what actually causes this solution to conduct electricity. As we mentioned repeatedly, the reason a solution will conduct electricity is because it has the ability to generate ions when it dissolves in water. Remember, as we learned previously, a non-electrolyte will not ionize at all. A weak electrolyte will ionize partially. A strong electrolyte will ionize 100%. So for the same concentration, a strong electrolyte will provide the largest concentration of the ions as a result of the ionization. So which one is the strong electrolyte? B is the strong electrolyte. Remember, strong electrolytes, you have strong acids, strong bases, and soluble salts. Weak electrolytes is going to be weak acid, weak base, etc. Non-electrolytes, you're going to have, for example, that's non-electrolyte. That's table sugar, by the way. Glucose, methanol, ethanol, they are all examples of a non-electrolyte. They will not conduct electricity at all because non-electrolytes do not ionize in water. Weak electrolytes do ionize, but they ionize partially. Strong electrolytes ionize 100%. Let's go back and look at the properties of water for one more time. This time, we're going to look at the reaction between water molecules. So when one molecule of water is reacting with another molecule of water, one water will lose proton or lose 1H plus. So let's say this water loses a proton. It will be considered as an acid if you lose a proton. And the other H₂O, if it gains a proton, according to Bronsted-Lowry definition, this will be serving as the Bronsted-Lowry base. The result is after the reaction, you generate 1 hydronium ion and 1 hydroxide. And this process is called the self-ionization of water or auto-ionization of water. This also shows you water can serve as an acid and a base. And this property is so-called amphoteric property because it can act as either an acid or a base. So previously we mentioned water is not an electrolyte. The reason is because water does not ionize appreciably. When we look at the exact numbers for the concentration in neutral water at 25 degrees C, you will find out the hydronium ion and the hydroxide, which are the products generated because of the self-ionization or auto-ionization of water. You look at the concentration, it's 10 raised to negative 7th molar. Water does ionize, but it cannot produce appreciable concentration. It's not concentrated enough to support the electricity conductivity. For this reason, water is not an electrolyte. It's a non-electrolyte. You do need to remember these concentrations. In water, the concentration for both hydronium ion, or you can simply write H+, in short, they have 10 raised to negative 7th. And the concentration of the hydronium ion and hydroxide will be 10 raised to negative 14th. Okay. In neutral solution, the concentrations of hydronium ion and hydroxide, they are exactly the same. In acidic condition though, the hydronium ion will have a greater concentration than the 10 raised to negative 7th, and hydroxide will have smaller than 10 raised to negative 7th. In the basic condition, it's the opposite. The hydronium ion will be in smaller concentration than 10 raised to negative 7th. Hydroxide will have greater than 10 raised to negative 7th. So 10 raised to negative 7th molar is a key number that you have to memorize. But do remember, no matter if it's neutral or not, in all aqueous solution, the product for the hydronium concentration and hydroxide concentration is always 10 raised to negative 14th. Let's do a calculation based on what we just learned. So calculate the OH minus in the solution and determine whether the solution is acidic, basic, or neutral. Remember, hydronium concentration, when it's greater than 10 raised to negative 7th, then it's acidic. If it's smaller than 10 raised to negative 7th, it's basic. When it's equal to 10 raised to negative 7, then it's neutral. So when we are given this condition, we can do the calculation of hydroxide as well, because we know the product of these two concentrations is 10 raised to negative 14th. Substitute the hydronium ion into this equation, okay? So then you can calculate the hydroxide concentration, which turns out to be 1.3 times 10 raised to negative 10th. Because the concentration of hydronium is greater than that of hydroxide, so this is an acid, or in other words, the solution is acidic. Okay. But before we do the calculation, we have already made the comparison, because we do know, hey, this guy is greater than 10 to the negative 7th molar. So we know this solution is acidic to begin with, even before we do the calculation. But of course, you can do the calculation of hydroxide, because we do know the concentration of hydronium ion and the hydroxide, the products of the two will be 10 raised to negative 14. So that's how we did the calculation. Next, we are going to talk about so-called pH and the POH. At 25 degrees C, an acidic condition will have pH smaller than 7. The lower the pH, the more acidic the solution is. And the basic condition will have a pH greater than 7. The greater the pH, the more acidic the solution is. At 25 degrees C, pH will be 7 for any neutral solution. Please note, the pH scale is actually a logarithm scale. Okay, so in other words, pH for any solution is defined as negative log of H plus. P is the same as negative log. So pH is a negative log of hydrogen concentration. Because of the logarithm, we know in math, if a pH change by 1 unit, actually the concentration will change by a factor of 10. For example, if pH is 4, the concentration for hydronium ion, or simply you might list the H plus, it's 10 raised to negative 4th. However, pH is 3, which is 1 unit different. The concentration for hydronium ion is going to be 10 raised to negative 3, which is 10 times bigger in concentration. If you change to pH to 2, then the concentration for H plus becomes 10 raised to negative 2. So 1 unit change, it will be 10 times different. 2 unit change, it will be, you compare to this 2, compare this to, you compare pH 4, hydronium concentration, and pH 2, that's 2 orders different, which means it's 100 times different over here. So 1 unit difference will have 10 times concentration difference. 2 unit will have 100 times concentration difference. If it's changed by 3 units, it will be 1,000 times difference in concentration. Let's look at a question. How many times more acidic is a solution with the pH of 1 than a solution with the pH of 4? Hey, remember, 1 unit difference gives you 10 times difference in the concentration. 2 pH unit difference gives you 100 times difference in concentration. 3 unit of the pH difference, which is the case over here because 1 and 4, you have 3 units of pH difference. That means it's 1,000 times concentration difference. E is the correct answer. A solution with hydronium ion concentration of 10 raised to negative 4 can be described as, hey, remember, hydronium ion concentration greater than 10 raised to negative 7th molar, so this is acidic. For review purpose, if this concentration, hydronium ion concentration H3O plus, if it's smaller than 10 raised to negative 7th, then this solution is basic. If this concentration is equal to 10 raised to negative 7th molar, then it's neutral. So that's what we need to know. Basically, in this case, because of the concentration of a hydronium ion is greater than 10 raised to negative 7th. So this is acidic. Let's look at another example. Calculate the pH of the solution and indicate whether the solution is acidic or basic. First, even without doing the calculation, we know the hydronium ion concentration given is greater than 10 raised to negative 7th molar. So this must be acidic. Can we do the pH calculation? Yes, by definition, as we just mentioned repeatedly, pH, P means a negative log. So H, you could write the H plus over here in place of the H3O plus. That would be equivalent. Let's do the calculation by substituting the hydronium ion concentration into this equation and use your calculator correctly. You will find out pH is 3.74, which is smaller than 7. This is the same conclusion as we already arrived by comparing the concentrations without doing the calculation. But this does make sense. It is an acidic condition after you have done the calculation of pH. What if you are given the pH? Can you calculate the hydronium concentration? Or we sometimes, as I said, you can use H plus to replace that hydronium concentration. Calculate the hydronium concentration for a solution of pH of 4.80. Mathematically, hydronium concentration is determined by this equation, as you see over here. It will be 10 raised to negative pH. So substitute your numbers in. Your pH is 4.80. So for this reason, you can simply write this equation over here. All right? 10 raised to negative 4.80 is going to be your hydronium concentration. After you do this calculation, it happens to be 1.6 times 10 raised to negative 5 molar. Let's look at another concept. It's related to the concept, POH. How do you do POH? Remember, P is the same as negative log. POH is negative log hydroxide concentration. Calculate the POH of a solution and indicate whether the solution is acidic or basic. When you look at this, even without doing calculation, we should know if this is acidic or basic or neutral, because this hydroxide concentration is greater than 10 raised to negative 7th. So this is hydroxide. So this thing is basic. But can we do the POH calculation? Sure, we can. POH is negative log of hydroxide. So substitute the hydroxide concentration in and you calculate the POH. That's 3.74. Do remember, pH plus POH is always 14 at 25 degrees C. So you can calculate the pH by 14 minus POH. That gives you 10.26. So we also arrive at the same basic solution as the conclusion. Similarly, with the POH, you can calculate the hydroxide concentration mathematically. For example, if I tell you the POH is 4.80, can you calculate the hydroxide concentration? Yes, you can. More simply, you just simply write this down. Okay, the hydroxide concentration is 10 raised to negative POH. It's 10 raised to negative 4.80. Okay, so hydroxide concentration will be, use your calculator correctly, 1.6 times 10 raised to negative 5 molar. So that's the hydroxide concentration. Of course, we have a lot more details over here for other purposes, but we do know hydroxide concentration is greater than 10 raised to negative 7th. So for this reason, this is a basic solution. Look at another example. What is the hydronium concentration for an aqueous solution when hydroxide concentration is 4.57 times 10 raised to negative 9th? You are given the hydroxide concentration. Calculate the concentration for hydronium. The relationship between the two is hydronium concentration times hydroxide concentration is 10 raised to negative 14th. So hydronium concentration can be calculated by 10 raised to negative 14th minus concentration of hydroxide. Substitute the number in for hydroxide concentration, 4.57 times 10 raised to negative 9th. And this will give us a correct answer as A. What is the hydroxide concentration in an aqueous solution of pH of 10.34? Remember, you are given pH. You try to find out hydroxide. We have two different ways to do it. Let's work on the two different methods. The first is, according to pH, we can calculate the POH, right? So pH plus POH is always 14. So for this reason, POH will be 14 minus pH. That means 14 minus 10.34. That gives you 3.66, and hydroxide concentration will be 10 raised to negative POH. That's 10 raised to negative 3.66, and this happens to be 2.2 times 10 raised to negative 4 molar, and B is the correct answer. Now we have another method. Okay, this is method 1. Method 2, you can actually calculate the hydroxide concentration according to this equation, because hydroxide concentration times the hydronium concentration, you will have this equation. But do remember, according to pH, hydronium concentration will be 10 raised to negative pH. Okay, so this will be 10 raised to negative 10.34. You see that? Okay, then you will be able to calculate the OH minus concentration by 10 raised to negative 14th according to this equation. Okay, 10 raised to negative 14th divided by hydronium concentration. What is hydronium concentration? Hydronium concentration is calculated to be this, right? So we substitute the numbers in. 10 raised to negative 14th divided by 10 raised to negative 10.34. This gives us the same answer, 2.2 times 10 raised to negative 4th molar. That also gives you B as the correct answer. What is the pH for 0.1 molar of HCl? When you need to calculate the pH, you need to calculate the H plus concentration or hydronium concentration to begin with. And remember, HCl is a strong acid. This means HCl will ionize 100%. So for this reason, the concentration for H plus or hydronium ion will be exactly the same as the original concentration for HCl, because it ionizes 100% when dissolving water. This is 0.10 molar. And the pH is defined as negative log of the hydronium ion concentration. So it's negative log of 0.10, and this gives us a number of 1.0001. D is the correct answer. Let's talk about one more concept before we conclude this chapter. The so-called pH buffers, they contain significant amount of both a weak acid, not strong acid, a weak acid, and the corresponding conjugate base, which means you remove one H plus from that weak acid. So if you have a pair of weak acid and the conjugate base, this will serve as a pH buffer, which resists pH change when the small amount of acid or base is added to the buffer. Human blood is a pH buffer, and in the healthy individuals, the blood pH is actually in between 7.36 and 7.40. If the pH were to drop below 7.0 or rise above 7.8, it's really dangerous. Death could result. Acid rain is a result of sulfur dioxide and nitrogen oxides, for example, nitrogen dioxide emitted by the fossil fuel combustion. These oxides, they can react with water to form acids, and they will fall as acid rain. And acids will dissolve metals and metal oxides, so the building materials composed of these substances are susceptible to acid rain. Acids can also react with something like a calcium carbonate. Acid rain all in all, is an environmental hazard that we need to avoid. So that's it for today. Have a good day. See you next time. Bye.